Hello and welcome back. In this video, we are going to look at overfit and underfit. And the dataset that we'll be using is the HIGGS dataset that has around 11 million records and 28 features. But for this particular video, we won't use all of that data. I think we'll just use 10,000 records. And as before, this code is directly from the docs. I will be copying the code from there and try to explain as we go through the code. And here is the link for the docs where this code is available. So the brief overview of what we are trying to do in this particular exam in this video is we'll create different models with different number of hidden layers, different number of units in each of the hidden layers, and then see how that results in overfitting. And once we have that, we'll try to apply regularization methods or dropout method to combat the overfitting that we would see in some of these models. So let's get started. And first step, as usual, is the setup where we'll import the libraries that we need. So let's do that. Let's import TensorFlow as tf. Then from TensorFlow .keras import layers. Then from TensorFlow .keras import regularizers. And we can print the version of TensorFlow tf.__version__, and this should get us the version. After that runs, the next thing we need to do is install the TensorFlow docs if it's not already installed. And the reason why it's taking so long is it's still initializing. So now it should run. We do have the RAM allocated. Let's see what resources we have. We have around 12.7 gigabytes of RAM and plenty of hard drive space. So let's go back up. TensorFlow, probably a typo there. Yep, that's what I thought. TensorFlow. And once we have that running, we have a version 2.11.0. The next thing we need to do is install pip install git plus https://github.com/tensorflow-docs. And following that, what we need to do is import the docs. So for that, we'll type import. All right, so this is already, I've already run that line of code, so it says it's already installed. Import TensorFlow_docs as tf.docs, and then we need import TensorFlow_docs.modeling and import TensorFlow_docs.plots. And next we need from IPython with a capital I and capital P import display from matplotlib import pyplot as plt. Then we import numpy as np. And then we have import pathlib, import shutils, util, import temp file. Okay, so with all the libraries now imported, we can set the path for the TensorBoard logs. A log dir is equal to path pathlib dot path with a capital P temp file temp_file.mkd make directory temp, then /::tensor board underscore logs, and then below this we have sh_util.rm_tree, then we have log dir comma ignore underscore errors is equal to true. So with that all set up, now we are ready to pull the dataset. And for, as we mentioned earlier, this is the HIGGS dataset, the HIGGS dataset. So we'll just download the data, download data, and for this it is a zip file that we need to get. GZ is equal to tf.keras.utils.get_file. Then we have HIGGS.csv.gz, then http, and then here we can specify the URL https://mlphysics.ics.uci.edu/data HIGGS/HIGGS.csv.gz, and that should download the file we are looking for, and it's going to take around 2.5 minutes, maybe less than that, 2 minutes. While that is running, we'll what we are going to do is declare a global variable features. So features is equal to 28, and then what we are going to do is we are going to read the data from the zip file without uncompressing the file, directly using the method tf.data.experimental.CsvDataset. And so for that, while this is downloading, we can go ahead and type out the command ds, that's the dataset, is equal to tf.data.experimental.CsvD and here we specify the name of the file gz.gz comma, and what are the features, what is the type of data in each of those columns in the features. So it's all going to be set to floats, so we'll say floats comma, and in here we'll specify how many times we would like that item to be repeated in that list. So we'll just specify features, which is 28 plus 1, that comes out to 29. And what that essentially does is, let's run this here, so we'll get an idea. Is what we have is just this list. If we ignore this part, what we have is a list that has an item float, open close parenthesis, and a comma. When we multiply it by any number, what happens is the items inside of that list are repeated those many number of times, and that's what we are trying to do here, is assigning this data type to each of the values in the columns as we import or as we read the data using the tf.data.experimental.CsvDataset. So here's what I was trying to say is this. So we get a list, and these are all floats initialized, and that's what we intend to do here when we are reading the file. So let's run this, and that's what we have. And if we look at the type of ds, now let's look at the type of ds. So that's the CSV dataset we have. Now we'll create a function. So we'll create a function. What this does, it repacks the list of scalars list of scalars from the CSV reader class, and then converts it into, and we kind of repacks this into a feature vector and label pair. And if you do not quite get this right now, it will be clear as we write the code below. Okay. So let's put that there, and this is the function def is equal to pack underscore row, and we have the input argument star row, label is equal to row 0, so that's going to be the label, the first value, and then the remaining will be the features. So feature with the s, features, is equal to tf.stack tf.stack, and the features are going to be row, and starting at index 1 all the way up to the end, and we put a 1 here when we are performing the tf.stack, and then we return the values. So return features label. So with this setup, we can now take our dataset ds that we have and map this function to that dataset. So ds.batch, and take a batch of 10,000, and to this we are going to map pack underscore row, and then unbatch that, unbatch batch, and this output we are going to put in the variable packed underscore dataset. So now when we look at the type of this, print type packed underscore dataset, here's what we have. We see that this is an unbatched dataset because we have the unbatched right here. And now once we have this created, we can look into the dataset and see what we have. So for features and labels in packed underscore ds dot batch 1000, we're taking a batch of just 1000 dot take open close parenthesis 1, and here we are going to print features at the index 0, so that's going to be the very first record, and plt.hist features.numpy, converting it to numpy array, and then flattening it, flatten, and bins is equal to 101. So when we run this, we should get a nice histogram. Well, we have an error, so let's figure out what the error is. For features labels, let's put a label there instead of labels. Feature label in packed underscore ds batch 1000, take 1, print features with a s, features flatten bins is equal to 101. Let's run this now. It shouldn't still matter. Okay, figured out what the problem was. Up here where we have the tf.data.experimental.CsV, here we need to put compression type is equal to GZIP, and after adding that we have this cell running, and once that run is completed, we should be able to see an example of what values are in the data set. Additionally, we should be able to see the histogram for that particular set of values. And here's what we have. We have the values, and looks like most of the values are between plus minus 2 with few values outside above 0 point, about positive 2 and few values below negative 2. Next, what we'll do is we'll set a few more few more parameters or variables, and this is just to so that we can reuse them because we are going to create several different types of models. So first is n validation is equal to int 1e3. Next we have n underscore train is equal to int 1 e to the power 4 buffer size is equal to int 1 e to the e4. Then we have batch size. This is equal to 500. And then we have steps per epoch. And this is equal to n underscore train double forward slash batch underscore size. Once we have these declared, now what we can do is we can create our train and validation data sets. For that, we'll define the variable names as follows. Validate underscore ds is equal to fact underscore dataset dot take n underscore validation dot cache, and train underscore dataset is equal to fact underscore ds dot skip n underscore validation dot take n underscore train dot cache. Yep. Open close parenthesis right after that. And with this, we now have created our train and validation datasets. So this is train underscore ds, and here we see it's a cache dataset that we have. Now we can also get the we can shuffle. We can attach the shuffle and the repeat and batch to this as follows. So validate underscore dataset is equal to validate underscore dataset dot batch size, and then train underscore dataset is equal to train underscore dataset dot shuffle buffer underscore size, and after that we have dot repeat, and then we have batch, and this is going to be batch underscore size. So what this is, what we have here is we have now the appropriate batches for training with the repeat and shuffle. Now we'll get started with creating different models as we started out listing them to demonstrate overfitting. And so the first model we'll create is, let's write the heading here, demonstrate overfitting. Now in this particular case we are going to repeat the same lines of code. So instead of repeating these codes several times, we are going to create functions. We call the function, it will do the compile and fit the model steps. But before we do that, there is one important detail, and that is the learning rate. How do we kind of gradually reduce the learning rate? And so for that, the learning rate, for that we are going to create an optimizer schedule. Learning rate underscore schedule is equal to tf.keras dot optimizers dot schedules or schedules inverse time decay and open close parenthesis. We set the value of 0.001, and then we have the decay underscore steps is equal to steps per epoch, and this is times 1000, comma, decay underscore rate is equal to 1, and then we have staircase is equal to false. That's the layer for scheduling. Next, there's a typo optimizer. I forgot to type the Z there. So that is good. Now what we can do is create a function def get optimizer open close parenthesis, and this is going to then return tf.keras.optimizers.atom lr underscore schedule, and so that's the function that uses the layer that we have created above. Now we'll create a plot to visualize how the learning rate gradually reduces or decays. And for that, we'll create a variable step is equal to np.linspace 0 to 100,000, and below this we are learning rate is equal to learning rate underscore schedule step, and then we have plt.figure fig size is equal to 8 by 6, and then we have plt.plot step divided by steps per epoch, comma, learning rate, and then we have plt.ylim, and within parentheses we have the word we have 0, and then max value of plt.ylim, like so. And finally we have the next level plt.xlabel epoch, and then we can say the plt.ylabel learning rate. And with that we can try to print this out, and here we have the plot. As the epochs increase from 0 to 5000, we see that the learning rate gradually goes down, and so this is what we are going to use in the models that we are creating, that uses the learning rate schedule. So the first function that we'll create is create callbacks, and the reason why we want to use callbacks is because we do not want to waste time to keep the training ongoing when it's not going to improve the results any further. And so there are 3 different ways we can stop the training ahead of time after knowing that further training is not going to be much helpful. And so for that we'll write this function get callbacks name, and here we'll return a list, and this list contains tf.modeling.EpochDots 1, then tf.keras.callbacks.EarlyStopping monitor is equal to validation binary cross entropy And then we have patience is equal to 200. And after that, we have tf.keras.callbacks.TensorBoard with a capital T, TensorBoard, log dir, and we have the name. So that's the callbacks we have, callback function we created. The next function we would like to create is the function that does the compiling and the fitting. So this is the compile and fit. df compile and fit takes in the model name optimizer is equal to none, max epochs is equal to 10,000. And in this function now, if optimizer is none, if there is no optimizer specified, then we'll say optimizer is equal to get underscore optimizer, and that's where it'll get this optimizer that we have created above. Next, compiling. So this is the compile part. Model.compile optimizer is equal to optimizer. The next thing is loss is equal to tf.keras.losses.binary cross entropy, and in parentheses we specify from underscore logits is equal to true, and after this from logits is equal to true, and then we have the matrix is equal to tf.keras.matrix.binary cross entropy open close parenthesis from underscore logits is equal to true, comma name is equal to binary underscore cross entropy, and second metric is accuracy. Okay, so now we have the model compile part ready, and the next thing is model summary. So we have the model dot summary, and finally we can write the code for fitting the model. The history is the variable that stores the information created during the training process. Model dot fit train underscore ds, and then steps per epoch is equal to steps per epoch, and then we have epochs is equal to max epochs, and then we have validation underscore data is equal to validate underscore ds. Let's put a comma there, and then we have callbacks is equal to get underscore callbacks with a s open close parenthesis name, and lastly we have verbose is equal to 0, and then with all this done we can finally say return history. So all this model is trying to do is create a model, compile it, compile the model, get the summary, and then fit it. So none a equals none. So my mistake, again a typo, that's in the line D, E, F, F, right here. This is NONE. And we have the function that is ready. With this all done, we can now write the code for creating the models that we have. The first model we'll look at is the tiny model that has just one hidden layer. So let's create that one. This is a tiny model. Here we'll create a tiny model using Keras sequential. Tiny underscore model is equal to tf.keras.Sequential, open close parenthesis, open close square brackets, layers.Dense 16 activation is equal to relu. And then we have input underscore shape is equal to open close parenthesis features comma. And then the output layer we have layers.Dense 1. And so that's the model. And we can create the histories. So size underscore histories, so that's a dictionary we are creating, and we'll put this model in there. So size underscore histories tiny is equal to compile and fit tiny underscore model comma sizes backslash / tiny. What we are doing is we created a dictionary that will store the runtime data while when we are training a model, and histories, and here we are creating a key tiny that will have a value that is output from the compile and fit, which is the history that is coming in from here, compile.fit. So let's now run this model, and so compile.fit and see what we have. Model is the undefined, and let's see why we have that error. So if we scroll back up, we're seeing models. Oh, and the reason is because I have put an S there, so that should be just model. So now when we run this, we should see epochs and the training of this particular model. So I'll come back once this is done, and before I end this particular video, this part, let's go ahead and plot the values. So plotter is equal to tf.docs.plots.history plotter, and this has input metric is equal to binary underscore cross entropy, and smoothing underscore standard underscore standard is equal to 10, and below this we have plotter dot plot size underscore histories, and plt dot y limit is 0.5 to 0.7. So this is now this will create the plot for us, and what we have are the epochs they are going through. So we have epoch 0, then we are printing the output every 100 epochs, and total we have set the epoch size to, we have 10,000 epochs. So this is going to take a while to run. So after this run is completed, I'll come back and Welcome back. And here what we have is after the run is completed, we went over a little over 1000 epochs. And after that, this is the plot where we can see the loss as a binary cross entropy that decreases with increasing epochs. And up to, let's say, up to 600 epochs, and there seems to be a decrease, maybe up to 700, but after that the validation loss kind of plateaus out, but the training loss still seems to continue to go down. But this is one nice example where we can see that as the training loss decreases, training loss continues to reduce, the validation loss also continues to reduce up to a certain point, and then it doesn't make any difference. So with the same setup, what we are going to do next is train the small, medium, and large models. And for that, what we need to do is create our layers. So I'm going to copy these and paste it here. So first we'll work with the small model. So small model, and for the small model, let's paste this here. Change the name to small, and what we need to do here is add another layer, which is layers.Dense, and here again we have 16 units, and activation is equal to, we are going to use the ELU activation, ELU, and same thing here. So that's our small model, and again to get our histories, we need to add another key value pair in the size histories dictionary by calling this as small, and again this is going to be the small model, and this again will be small. So that's the small model, and likewise we'll go ahead and create all the models and then run them in one go. So there's a create another model, and this is going to be medium model. And for medium model, again, what we'll do is copy the same lines of code right there. And the difference here is going to be that we are going to add one more layer for the medium model, comma, and here Mr. Comma, so we need to put a comma there. And the model is going to be the same with the same layer repeated here, and the units are going to be 64 instead of 16 for the medium. And again, this is going to be a medium model, so we change that here, and instead of small we call this as medium. Likewise, this is going to be medium. Once we are through with this, the next thing we need is the large model. And for the large model, again, let's create a heading. Let me copy this, and we'll create a heading large model. So large model, and then we paste this here, call this large. And for large model, what we have is we'll add another layer in addition to the 3 layers we had above. So these are going to be 4 layers, and instead of 64 we are going to use 512 units. 512, and the activation is still going to be ELU for all 4 of these. And finally we need to add the history. So the key value pair that we'll add here is going to be large, and again for medium we'll set this to large. Here this will set this to large. So we have a large model, medium model, and the small model. So why don't we run this, and after the run is done and hopefully there are no errors, I'll come back and we'll look at the plot, how we can create the plot to look at the decay in loss or the number of epochs. So let's run all of these. And while these are running, I'm going to I'll stop the video now and come back when all the runs are done. Welcome back. here all the three models are now run. We have the small model, which where the loss goes from 0.7 to zero point 0.5 for the training set. For medium, it goes from 0.6 to zero point 0.4. And then for the large model, it goes from 0.7 to 0.0001. So that looks like this may be overfitting here because we have accuracy on this. So this has to be overfitting. Now, the next task that we have is to visualize the loss with the progression of the epochs, and we'll create a heading here which says plot the training and validation losses, and for this we'll use the lines of code as follows: plotter.plot size underscore histories, and then we have a is equal to plt.x scale log, and then we have plt.xlim 5 comma max of plt.xlim open close parenthesis, and then plt.y limit is going to be 0.5 comma 0.7, so 0.7, and plt.x label is going to be epochs, and then within square bracket this is a log scale because we have specified that this is x scale is log. And now let's run this. Hopefully we should see a beautiful plot as we do here, and let's zoom in into this, and what we see is, as first of all, this is the earlier one, tiny train. That's the one that we saw earlier. Now after that, let's look at the small train. So small train, again, as we see, the overfitting starts, this model starts to overfit somewhere down here, because you can see that the training loss continues to steadily decrease, but then the validation loss plateaus out. And then if we look at the medium train, which is the line in green, the overfitting starts pretty early on, right up at this point, where we can see that maybe right up here. So the training loss continues to steadily decrease, but then our validation loss ramps or increases. So that's like classic overfitting we have. And then again, if we have a large model, as we see here, in case of the red line that is shown, we see that the overfitting does happen early on again, and the validation loss increases rapidly as the training loss continues to decrease. So to combat this, what can we do? And we'll look at that in a moment. But before we go there, let's look at this option in TensorFlow where we can view results on the TensorBoard. And for this, here is the line of code that we need to type: %load underscore ext TensorBoard, and then %TensorBoard dash dash log dir open close curly braces log dir, and then / sizes. So let's run this, and this will launch the TensorBoard. And once that is through, so we should see it somewhere here. Okay, so once that is done, we will, okay, so here is what we have. So that's what we see. We have these on the x-axis and y-axis. We have the epochs on the x-axis, and what do we have on the y-axis? We have the accuracy on the y-axis here. And just as we saw earlier, this is the plot for the loss. But with the x-axis we have the number of epochs, and the y-axis we have the binary cross entropy listed. So that's how we can look at the results in TensorBoard as well. And in TensorBoard we can change these options to kind of change the display that we have up here on the screen. So in addition to this, what we can also type is this display.iframe open parenthesis source src is equal to and then we'll specify URL https://tensorboard dot dev /experiment /vw7 jmm so this is what I'm typing right now is the display that is from the docs. So why don't I do this? I'm just gonna copy this line of code here and paste it, and then say width is equal to 100%, and then we have the height is equal to 800 pixels, and then run this. So there's an error iframe src. Let's see what the error is. So yep, my bad. Here we need a single quote. Now run this, and when we run this, we should see an output, and here is the output with the similar results. Here we have the epoch accuracy on the y-axis, and we have the epochs on the x-axis. Likewise, we have the similar results here in this particular chart. So what we are doing here is we are pulling the results that are from this particular URL, and in the earlier case what we had was the results that we had just seen in the training that we ran above. Now let's move on and look at some of the strategies to prevent overfitting. So why don't we create a heading, strategies to prevent overfitting with an N. And here what we are going to do is we are going to look at L2 regularization and dropout. So before we do that, let's create copies of directories. So for that, this is the code you want to write. Shutil. So what we are trying to do is we are going to copy the training logs from the tiny model and use that as a baseline comparison. And for this we'll use the shutil dot remove rm3 log dir / regularizers tiny, and then comma, ignore errors is equal to true, and shutil dot copy tree log dir sizes tiny, and then we have log dir / regularizer with a s tiny. Run that. Okay, so we have that set up. Next we create a dictionary, a regularizers history, regularizer underscore histories, and to this dictionary we are going to save the inputs after we perform the regularization steps. Regularizer underscore histories tiny, and this is the baseline key value pair we are adding here based on the training that we have already done. Histories and with the word tiny. So the very first one is L2 regularization. So we add that here. Add weight regularization, and this is going to be L2 regularization. And for this, what we are going to do is use the model that we had created above, which is the large model. So I'm going to simply copy the code that we have, this code, and we'll modify it a little bit to add the L2 regularization in there. So here we'll change the name to L2 model, and the layers that we have, we would still have the 4 layers with 512 units and the same activation function. The only change we will be doing here is we'll add an argument which is a regularization. So let's do that. Bring this down one more, and then here we'll add kernel regularizer is equal to regularizer with s dot l2, and we'll set the value to 0.001, and then that's what we have added. And we'll add this line to each of the layers that we have described below. So that's 1, then that's 2, and then that's 3. So what we have are the same set of layers, except the difference now is we have added the regularization to each of the 4 hidden layers that we have in the model. And so I'm hoping this is all good. Or there is a red line there, so wondering if I'm missing a comma somewhere. Let's look at these. So that looks okay. Alright, let's run this and see if it throws an error. So that looks okay. The next thing we'll do is we'll add a new key value pair to the dictionary that we created above just now. Regularizer underscore histories open close square bracket L2 is equal to compile and fit L2 underscore model comma regularizers L2 and run this. So here is the model summary we have, and then this is the model that is being trained, and we see that we start out with a loss of 2.2 for the validation. Oh no, not the validation, for training, that's validation loss is 2.08. And once this is done, we should be able to plot the results. So let's go ahead and type that out. Plotter.plot regularizer underscore histories, and we'll say plt.y limit 0.5 comma 0.7, and hopefully we should be able to see the results of this L2 regularization right here. And once this is done, we'll move on to the next step, which is L1 add dropout. So we'll let this run for, it may take a couple more seconds to run this, and we can see that the loss has dropped quite a bit to 0.5, and so that's what we have so far. Next thing that we'll be doing is adding a dropout. Okay, so here is the result we have, and as you can see, the loss is definitely much lower as compared to loss is much lower as compared to what we had in the tiny train, and the validation loss again plateaus at just above 200 epochs, while the training loss continues to decrease. Next, what we can do is we can save the results in the variable result is equal to L2 underscore model features, and then regularization underscore loss is equal to tf.add underscore n L2 underscore model dot losses. Run that. And now what we'll do is add the dropout layer. We'll work with the dropout layer and then create a combined model with a regularization and dropout both. So this is just the dropout. Add, let's add one more hash there, add dropout, and we do not need that A. I'm going to remove that, and let's go back up, copy the code that we had for L2 model, and just modify that code for the dropout. So let's bring this down and paste it right here. I'm gonna zoom out a little bit so we can see the entire code. Okay, so the first thing we need to do is change the name. This is going to be dropout, and what we do in dropout is convert the values in some of the layers to 0. So dropout, we are setting the values to 0, a number of output features of the layer during training. And what we are going to do is leave the file as is, leave the activation as is, and then we do not need this part, so I'm going to remove it and leave that as is. Again, we do not need any regularization in this case. I'm going to remove the regularization from all the layers, and instead what we are going to do is add a dropout layer. So layers dot dropout, and this is 0.5 comma, and then we are going to copy this and paste that here, paste that here, and paste that here. And finally, for the histories, let's go back up and again copy this line of code, which is simply going to be the way we are going to add the key value pair to the dictionary which stores the histories. So regularizer histories, and we'll change the key name to dropout like this, and this model is going to be again different. It is going to be a dropout model, and likewise this name here is going to be dropout. Okay, so with this all set up, let's go ahead and run these lines of code, and we should see the training as it progresses, and finally we should be able to see the plot. So why don't we type the code for plot, as this is training. Plotter dot plot regularizer underscore histories, and again we need to set the while limit. While is 0.5 comma 0.7, and once the training is done, we should be able to see the plot for the losses. That's a binary cross entropy for both. This is going to be L2 and dropout, along with the tiny train baseline that we had created above. And let's see what we do we see any improvement, or do we not see any improvement as compared to the baseline that we have already trained earlier in the beginning of this video is that with both L2 regularization and the dropout, they seem to do better in terms of avoiding overfitting as compared to the large model that we had trained earlier. But still, the tiny model seems to be performing better in terms of avoiding overfitting, because here we see that as the training loss continues to decrease, we are starting to see overfitting because the validation loss is increasing, the binary cross entropy is increasing. Next, what we'll try is combine both the dropout and the L2 regularization and see if that improves the model further as compared to the large model, or and maybe the baseline that we are looking at, which is the tiny model combined, and this stays as is. In addition to this, what we are going to do is add a dropout layer, and for dropout it's simply going to be this layer that I'm going to copy and paste it after each of the hidden layers that we have, which is going to be right here for the first layer. Then for the second layer we have this right here. After that, for the third layer, this is going to be right here, and finally the fourth layer we have this right here. And likewise, we can also copy the line of code for the compile and run part, so add that here. And this is going to be combined, so I'm going to change the name to combined, and again the model is going to be combined, so change that. And finally here we add the word combined instead of dropout. So once we have this all set up, so I think we are good to run. There is some lag on the screen right now, so please bear with me for that. I'm going to add few more cells here, and also add the code to create the plot. So why don't we just copy that from up above. So I'm still waiting for this screen to respond. For some reason it is extremely slow right now, but give me a couple of seconds. And oh well, it's taking quite long now. Okay, so I think we are getting there. So let's copy the line of code for plotting, which is here, plotter.plot, and paste it down below. So that's the block we need. So I'm going to copy that and then scroll all the way down and paste it right here. And once we have that in place, I'll go ahead and run all the three cells so that we can see all the plots. Okay, so let's click on that and then run this cell, and this cell. There may be a lag, as you'll see in the video, but hopefully we should be able to see the final plot with the overlay of the three different models for regularization as compared to the baseline tiny model that we have looked at earlier. And so we'll wait for that to happen. And I'm hoping that we see some improvement with the combined model as compared to definitely the large model, and maybe even better than the L2 by itself or dropout by itself, and the tiny model. That would be the best thing if it does better than the tiny model. So let's wait and watch. And you could forward this part. I'm going to continue recording until this training is done. So 400 epochs. The earlier model, it took, let's see how many epochs did it take to run the earlier model. and I think it went up to what, 600. It stopped at 300. So that stopped at 300. This might stop at around somewhere around there. Okay, so here we have, so it stopped at around somewhere above 400, and we can see that in this case, again, this is the combined model. The combined model is this one, which is the pink color, and the loss is still higher in this case. I wonder why. So we have combined model, and wondering what's going on with this one. So we have the 512, 512. We have that 0.000. Okay. So I'm looking at the docs, and the L2 regularizer here, the value used is 0.001, so 3 zeros and 1. So I'm going to change that uh, and add another 0 there, because if you look at the output we have, the validation is kind of worse than the baseline. I mean, it's a much yeah, higher than what we had for the baseline. So let's see if we change this value for regularization, if that makes any difference. So I'm going to go ahead and run this again, all the cells, and we'll see if that makes any difference in the final output that we have. So again, this should run through the 400 plus epochs, and after that we should be able to see the output. And this is the final plot in this video, just waiting to see what results we get. And it's a couple more seconds. While this is running, I just wanted to say that if you have any comments or suggestions on these videos in TensorFlow, please do let me know in the comment section below, and I'll try to see if I could create videos on those topics as well. So the binary cross entropy is 0.7. It has come down to 0.5, and this looks like this is working because earlier these values didn't change much, but now we are much below what we had earlier for the tiny model. We're at 0.57, maybe quite about the same so far, 0.56. If we scroll back up, maybe not. There's a lag again on the screen. So this is 700 epoch, and the loss is steadily decreasing, but it is now starting to plateau, as you can see. It was 0.60 for these many epochs, and then it is now not changing much, 0.59. But initially there was a significant drop from 0.95 to 0.63. So that was good. And if we look at, okay, so looks like the plot is almost ready. And here is what we have. We see that by changing the learning rate, we were able to again bring down the loss of training loss as well as the validation loss. And in this case, this seems to be the best model we have so far, with the with two two methods combined. The first is L2 regularization combined with dropout, that seems to have kind of taken care of the overfitting problem that was with the large model that we had created with 4 hidden layers and 512 units. So after this, it's the same way we looked at earlier. We could look for the same plot visualization in TensorBoard if you want to give it a try. We'll skip that in this video. If you have any comments or suggestions, please do let me know in the comment section below. I really appreciate your likes and support that you are showing on this series, and that keeps me motivated to find more topics and create more interesting tutorials for you all in this series. Thank you and hope to see you all in the next video. Bye for now.